Alrighty, and I guess welcome to the afternoon, the last session of the afternoon.
Hi, I'm Nolan Lake. I'm the co-founder and CTO of Cumulus Networks.
And I'm Mark McLean. I'm co-founder and CTO of Aconda. So let's kind of talk a little bit about where we're going to be headed today. We're going to kind of talk a little bit about Neutron with VXLAN, kind of talk a little bit about the problems and challenges, some of the alternatives and solutions available. Then we're going to kind of dive into what a real-world deployment looks like and what we've been working on the last couple of months, and then finally take a look at the conclusions from deploying the solution in the real world. So, kind of to kick it off, we're going to kind of dive in, kind of level set, go with a few of the basics on, really Neutron's story with VXLAN. But before we do that, we kind of have to take a real quick primer on ML2 just to kind of make sure we got all of the primitives down. And so, we've probably all heard of the Modular Layer 2 plugin by now. It's a full implementation of the plugin. It has two types of drivers. One's a type driver, which is, common interface for all segment types. It manages the specific resources. If you have a VNI, it's going to handle the selection, or if it's VLAN, it'll handle the ID. And type drivers are extensible, so you have type drivers for, local networking, which is really for testing, flat networking, so you can tie in with existing infrastructure in a data center, or VLAN if you have pre-provisioned VLANs, GRE, VXLAN, and now Genev's available. And the other driver is the mechanism driver, which is really for ML2, which is where a lot of power comes from, because it's what enables you to connect in with back end. So it's a common interface. It manages the specific elements of communication, and it supports multiple drivers, so you can have a multi-vendor strategy. And in Liberty, it's extensible, so that you can implement some of the extensions and expose them both from ML2 perspective, and also some extensions which may not, which may be unique to a particular solution.
Okay, so I'm going to start with a little bit about VXLAN. So VXLAN is a protocol and technology that's used to encapsulate layer 2 packets in layer 3 packets. And so the reason you want to do this is it allows you to create layer 2 networks on top of a layer 3 fabric. And that's important because layer 3 or IP fabrics scale, right? The internet is larger than any data center anyone will ever build. And so using the same technologies that make the internet work, you can build very scalable and very reliable data center networks as well. And so the key one for these purposes is ECMP, which is equal cost multipathing. And it's important because now all of those links in a densely interconnected network are active at the same time. Traffic can go over all of them. And this gives you better, more predictable latency, higher bandwidth obviously, and faster error handling. Because you already have connectivity. If one of the links fails, it's just withdrawing it from service, as opposed to if you're using an L2 technology like STP, where you have to do a lot more calculation to figure out the new path the packets are going to take through the network. There's another solutions people sometimes use for this, for building layer 2 networks, which is called MLAG. It has its own disadvantages. It's proprietary. There's no standard for MLAG. It's a very complex thing to do. You're essentially intentionally creating loops in your L2 network and then doing a lot of dancing to keep that from melting your network down. And typically, you can only have 2 switches in an MLAG pair with most implementations. So that limits the total amount of bandwidth. It creates a bottleneck. And so I talked about these point-to-point tunnels, and so if you're experienced with layer 2 networks, that probably kind of triggered something, which is, well, how do I handle traffic that's not point-to-point? And so we call that BUM traffic, and it stands for broadcast, unknown unicast, and multicast. And so broadcast is traffic that is destined for everyone on a given network. Unknown unicast is if you don't know the destination of the network. The way layer 2 works is you flood it to all possible destinations, which is essentially the only way to guarantee it gets to its real destination. And then multicast, which is where it's similar to broadcast, but instead of going to everyone, it goes to only the endpoints that have expressed interest. And so there's a couple of different ways we can handle this, and we'll get into which one we chose later. The VXLAN standard talks about multicast. Basically, on the physical network, you create a multicast group for each logical L2 network. And so now anyone who's participating in that L2 network can register as interested in that multicast group. And so they'll only get the bum traffic for their layer 2 network. The other way, which we've talked about, Mark and I have talked about at previous summits, is a software replicator. And the idea there is everyone who's encapsulating VXLAN traffic, when it sees one of these bum packets, instead just sends it off to a special replicator, which can be just software running on an x86 server or any other place. And what it does is then replicates the packet to all of the different, unicast replicates the packet to all the different listeners that are interested in it. And the final one is what we call head-end replication. In this model, every device that is encapsulating VXLAN traffic can also replicate to all the interested listeners. And it can do that in hardware. So if this thing, well, if it's a switch, it can do it in hardware. So there's a couple of different ways you can deploy VXLAN with Neutron. The kind of default one is doing VXLAN in the hypervisor. And so we talked about the L2 packets being encapsulated in these VXLAN packets. In this case, that actually happens in the vSwitch. And it happens in software. So this can create some performance issues because now the software is having to append this header, basically poke on each and every packet that goes by. And the big thing about networking is, to get performance, you want to make sure that software doesn't have to look at each and every packet. You want something else handling each and every packet, and software just setting kind of rules for how to handle the packets. And the other problem is that you end up with a huge number of VTEPs. Now, the VTEP is a VXLAN tunnel, VXLAN termination.
Virtual tunnel endpoint.
Virtual tunnel endpoint, thank you. Acronyms everywhere. And you end up with one per hypervisor node. So if I have 32 racks, each with 32 servers in them, you end up with 32 times 32 VTEPs. And so the numbers scale up pretty quickly. And since it's happening in the vSwitches, there's nothing you can do easily to bring in devices that don't have a vSwitch. So bare metal servers, hardware appliances like load balancers and routers and things like that cannot be connected to the logical networks, only VMs and containers. So the other way to do this is to do the VXLAN encapsulation and decapsulation in the top of rack switch. And so this is interesting because it gets you hardware acceleration, right? If your top of rack switch supports the feature, which most new ones do now, you can have it in hardware take the L2 packet, put that VXLAN header on it, and send it along to its destination. And so having hardware do something on each and every packet is absolutely fine, because it can do it all at line rate. Another cool thing is now the number of VTEPs scales with the number of racks. Instead, if I have those same 32 racks with 32 servers each, instead of having 32 times 32 VTEPs, I just have 32, one for each of the top rack switches in those racks. And we can now bring all of those non-virtualized devices into the logical network. So your bare metal servers managed by Ironic, hardware appliances, and so on. And so the feature that allows us to do this is one that showed up in Neutron in Kilo, and it's called hierarchical port binding, which is kind of a mouthful. But basically what it means is that you can have multiple different segment types, in this case a VLAN segment type and VXLAN segment types, and they will be merged using a ML2 mechanism driver. So the ML2 mechanism driver knows how to talk to the switch, the top of rack switch, to tell it to connect this VLAN going on this front panel port to a hypervisor to this VXLAN, which is going to then traverse the IP fabric. So I feel like I've talked a lot, so maybe a diagram would make this clear. So here you can see the kind of leaf spine layer. We've elided most of the leaves just to make the connectivity a little less insane with all the lines. And so you can see, we've got a build here. You can see the first hypervisor has chosen VLAN 37. So the traffic for a given VM coming out, or a specific VM coming out of this, will be tagged with VLAN 37. It will then hit the top of rack switch, which will then have the VLAN tag removed, and then have a VXLAN header added. In this case, it's chosen 2003 as the VNI. And so these numbers can actually be much larger than VLANs, which are limited to 4,096 different tags. These can actually be up to 16.7 million. And then the packet will traverse the spine layer, which is all layer 3, and land at the other top of rack switch. And in this case, the same virtual network has been allocated VLAN 55 on this switch. Now, if you're a traditional networking person, this is probably really weird to you because VLAN numbers are supposed to be global because it's a virtual LAN. But in this case, since the layer 2 boundary never leaves a single rack, you can reuse the VLAN numbers. In fact, in our case, you can use the reuse VLAN numbers between different front panel ports. So you have the full 4,096 VLAN numbers for each and every hypervisor, which should be enough for decades. So now we're going to talk a little bit about a real-world deployment. In this case, this is done with DreamHost and their new Dream Compute cluster. So they built the network on white box or bare metal switches running Cumulus Linux. So for those of you who don't know, Cumulus Linux is a Linux distribution based on Debian that runs, instead of on x86 boxes like your laptop or your server or your desktop, it runs on switches. And so a switch is basically just a fairly standard-looking server with one very special part, which is a forwarding ASIC. And so that's what allows it to do 32 ports of 40 gigabit per second bandwidth at line rate. And Cumulus Linux, unlike most traditional network operating systems, does not have a proprietary CLI. The way you configure it is the same way you configure Linux switching on a hypervisor. Use the standard Linux tools, IP route 2. You can do IP route add and then type out your little command. You can use brctl to create a bridge and to put ports into the bridge. So on a hypervisor, you would take a tap device and add it to it, create a bridge device, usually called BR0 or something like that. Create the tap device from the VM, put that into the bridge, and then you can bridge that to ETH0, for example, to connect that VM to ETH0. So those exact same tools work on Cumulus. But behind the scenes, what we're doing is we're hardware accelerating all that. So in a hypervisor vSwitch, all the packet forwarding is being done in software. All those forwarding decisions are made by software. In our case, we programmed the hardware, that forwarding ASIC I talked about, to do in hardware what Linux would have done in software. So this is similar to if you have a graphics, if you're old like me and you played video games in the 90s, you used to have software rendering and it would draw the little game world that you were playing in 3D. And then along came hardware accelerators and you dropped one in. Everything looked pretty much the same, maybe the graphics got sharper, but everything was way faster because it's being done in hardware. So basically, you can think of a switch running Cumulus Linux as a Linux box that just happens to have a huge number of 40 gig or 10 gig or 100 gig interfaces. A kind of relatively common switch today would have 32 40 gig interfaces, and so those would just show up as 32 Ethernet interfaces.
So on top of the layer 2 provided by Cumulus and Dream Compute, Conda is being used to implement layer 3 and above. So what we've done with Conda is Conda provides a layer 3 plugin. It's providing routing via service VMs, and then also provides additional services such as DHCP, metadata, and then coming soon, implementations for load balancing, as well as, and it's all based on the open source Astara project, which is the newest entrant into the OpenStack big tent. But Conda, while being the newest project, was developed at DreamHost in 2012 and has been a project that's been in production for a while in Harden. And so it enables, changes like this because of, rolling out a new architecture as well as transitioning off the old one that was used in early deployments of Dream Compute. The OpenStack environment, is based on the stable Kilo release. It is using ML2 drivers designed for hierarchical port binding. And essentially it's kind of what Nolan touched on a little bit earlier with the hierarchical port binding is where you have VLAN between the server and the top of rack switch, and then you have VLAN or VXLAN between the top rack switches. So it's essentially kind of the exact kind of sample case for hierarchical port binding.
So I talked a little bit earlier about the concept of IP fabrics and the advantages there. So I figured we could have a diagram, it might make it a little clearer. So this is a leaf spine or fat tree in the terminology. And so in the Dream Compute case, they have chosen 32 by 40 gig switches for the spine layer. And so what that means then is since there are 32 front panel ports on those spine switches, there can be up to 32 racks because each spine switch needs to connect to each rack. And so this scale's pretty big, right? 32 racks full of 1 RU servers can get a pretty high number of servers, and then with all those VMs on there, you end up with a fairly large number of endpoints. And the other cool thing about the leaf spine or fat tree architecture is that it's very scalable. So we've shown right here a zero overcommit network. And what that means is that any server can talk to any other server at full speed. So in a overcommitted network, two servers in the same rack can talk to each other at full speed because they're connected to the same switch. But if you then have to talk to a server in another rack, you're going to be going through a congested core switch. And so that's going to slow you down. Depending on the overcommit factor, common ones can be 5 to 1, even 10 to 1. I wouldn't recommend that. So you can look at it as if I have 10 gig connectivity coming on my server and I'm going through a 10 to 1 overcommit core, that means I can talk to other VMs in my rack at 10 gig, but the rack next to me I can only talk at 1 gig. So I have to be very careful about where I place my workloads so that they can communicate with the other collaborating servers that they need to talk to. So going back to the BUM packets, I talked about the different options, but now I'm going to talk about how we drill down on how we did it in the DreamHost deployment, Dream Compute deployment. We decided to use head-end replication. We wanted that hardware acceleration of the packet replication. We didn't want to have that done by software. And so that means we were doing the replication in the top-of-rack switches, because in this deployment, that's where the VTEPs are. So the VLAN tag packet goes up to the top-of-rack switch. It's not a unicast packet. It needs to go to multiple destinations. So then the hardware looks up the list of destinations and sends one copy of it unicast to each of those destinations. So now the IP fabric side only ever has to see unicast packets. And so I kind of glossed over something there. I don't know if anyone's going to call me out on it, but I said it replicates it to all the other endpoints that need to know about it. But how did it know? So the answer there is a pair of very simple Python programs that we wrote. They're open source. One is called VXRD, which again is kind of a mouthful. We like these kind of mouthful acronyms for some reason. And so that's the VXLAN node registration daemon, which is probably clear as mud. What it does is, as a VTEP, it keeps track of which virtual networks, which VNIs in the terminology, this particular VTEP is interested in. And so that means, in our case, this specific case, what virtual networks are connected to VMs that live in that rack. And so what it does with that information is it sends it to the VXSND, which stands for it doesn't stand for anything really. It's the VX Node Database Service. And so what it is a simple program that runs in, it can run anywhere. In this case, I'll get into that. It collects all that information from all of those VXRDs. So now it knows it has a global database over all the VTEPs of which VTEPs are interested in which VNIs. And then it pushes that information back down to the VXRDs. And so now the VXRDs know, hey, for all the VNIs I care about, all the ones that are associated with VMs running in my rack, here's the list of other endpoints that are interested in it. And that's all the information it needs to program the hardware to do that replication at line rate. So I kind of glossed over where they run. In this deployment, it's actually extremely straightforward. The VXRDs run on the VTEPs, which are the leaf switches or the top-of-rack switches. The VXSNDs, to reduce the complexity, we just figured, hey, run them on the spine switches. Cumulus Linux switches are just Linux boxes, so any software that runs on Linux and on a Linux server, you can run on the switch. And so in this case, I think we drew it kind of as every spine switch runs it. Typically, in a normal deployment, you'd run it only on 2 or 3 spines. You could run it on more, but they're not particularly resource intensive. You only need more than one for high availability. And if you lose more than 3 spines, you probably have other problems.
So one of the questions that comes up, hierarchical port binding is really a mouthful. Is it really complicated to deploy? And if you take a look at the config file, that's actually the entire config file necessary for ML2 and Neutron. It includes both the plugin and the agent file all collapsed into one. So if we kind of walk through it, you'll see, basically at the top, we're just saying our default network is VXLAN, and then we go through, say, the type drivers we want available, and then the mechanism drivers. And if you notice, we're running both Cumulus and Linux Bridge. Reason we have both those mechanism drivers enabled is because with hierarchical port binding, you're going to have you have to bind each of the segments. So the Cumulus drivers will take care of binding the VXLAN in the switches and notifying the switches. The Linux Bridge driver will take care of notifying the hypervisors which VLAN ID has been selected and pass that information along to the agent. Within that, you just have your standard configurations for what the network, what's the physical network name within the rack, which we just called RackNet. which ranges are available to be used, and then there's going towards the bottom, you have a little bit of extra information in terms of for the agent. Basically, you've told the agent that VXLAN's not being enabled because one of the challenges with Neutron is it's so configurable that sometimes you can turn on a couple configs and you have to turn some things off selectively, which is why you'll see VXLAN enabled false when it's actually on for the Cumulus. And then you'll see down there's the VLAN information, which has a little bit more specific information, as well as for the bridge itself, you have the physical interface mapping. So within the actual hypervisor, it maps the physical network name onto the actual interface. And then lastly, it's just a collection of when it's time for the Cumulus network driver to notify the switches, it's going to basically call out the APIs, and that's the last kind of config. But I mean, really that's it. It's amazing for something complex that the configuration is really simple.
Yeah, I mean, this configuration here is, almost all of this is boilerplate. You know, things like enabling the firewall driver, you know, that any ML2 configuration is going to have that. Similarly, you know, the agent, you know, root wrap and things like that. That's pretty much everything. The only things you have to customize is if you want to use a different VLAN range in that top rack to hypervisors, you can change that. There's no real need to. And the other thing you have to change is you have to put the IP address of all the switches, all the top of rack switches in that last part, the ML2 Cumulus part, just so that ML2, the Neutron server, knows how to talk to all the switches. But pretty much all the rest of this you can cut and paste right in. So, you know, that's just one part of the solution, though, of course. We still have the VXSND, which, given its great name, you may have forgotten, this is the database server. And so its configuration is very simple. It basically needs to know its own IP address so it knows what interface to bind on. We could just have it bind on all interfaces, but you know, for, I guess, safety or cleanliness, we like you to specify a specific IP to bind on. And then you enable VXM listening. So this is for a different mode. If you're using this thing as a software replicator, you set that to be true. In this case, we're not using software replication, so you set it to be false. And then the agent that runs on the switch, which you know takes these commands from ML2 from the Neutron server, also has a pretty simple configuration. In this case, we've thrown cleanliness to the wind and bind to all ports and all interfaces, and we've specified port 8140. I believe that actually might be the default, so we may not have even needed to specify that port there. And then we tell it what local interface to use for originating VXLAN packets. So this is the IP address to use for originating VXLAN packets. So for those unicast packets that get encapsulated, this will be the source IP. And similarly, for those replicated packets, this will be the source IP. And the final piece is you have to tell it which interfaces to ignore. In this case, ETH0 is the management interface on the switch. And so obviously we're not going to be sending VXLAN packets out of that because we're only using that to manage the switch. And the other is SWP1. In this config fragment, we only have one port going up to the fabric. In a real deployment, you would have a few more interfaces there. We're going to clean that config up a little bit. I think we can eventually get this down to just the local bind. And then the last piece of the kind of Neutron-specific part is the VXRD. This is that registration daemon. This is the one that runs on the VTEPs and tells the database what VNIs it's interested in. And so in this case, we need the service node IP. That's the server running the database server. And then we need our own source IP to bind to and to use when sending the packets up. And then the last part is that head rep equals true. That's turning on head-end replication. If you're using software replication, you'd set that to false. And then the last piece of the puzzle, you know, I talked about an IP fabric. Sometimes people get a little, you know, freaked out about routing protocols. This is the entire routing protocol config. You know, you may not recognize some of these commands. That's actually A-OK, because you can just cut and paste this whole thing. You probably want to change the password. And you might need to fiddle with the interface names if you plug things in differently. And you'll have to pick your own ASN, which is the address space number. The good news about that is you don't need to know what that means. You just need to pick a number there and use it everywhere. And then the last piece is that IP address. That's the only piece that needs to change for each and every switch. So if you have some templating engine or some automation tool, it is extremely easy just to blow out this template, changing that IP address on all of the spine switches and all of the leaf switches in your network. And so, results. So we did all this work. What did it buy us? So one, we've moved the VTEP to the hypervisor top of rack. So, you know, we've greatly reduced the number of VTEPs in our system. And so you may be wondering, okay, that's kind of cool, but what did that buy us? Well, it increased bandwidth a little bit. Before, with the software VTEP, you can get about 2 gigabits per second using VXLAN. And the reason for that, without getting too deep into the gory details, is a NIC feature called TCP segmentation offload. The big problem is most NICs today don't know anything about VXLAN, but they do know about VLANs. So this optimization has to be turned off when you're using VXLANs, but can be left enabled when you're using VLANs. And so it's apparently a pretty significant optimization because it gets you a good 4 to 5x speed increase. And it's proven at scale. You can build fairly large networks out of this. I think it's pretty much as large as you'd want to be a single OpenStack cluster. And it allows you to fully utilize your capacity. By building an L3 fabric, an IP fabric, you can use ECMP to enable all of your links, the ones that something like spanning tree protocol would disable in a layer 2 network. So that's it. Any questions? Do we have the microphone?
We'll repeat it.
Yeah, we'll repeat it.
Yes.
How do we do L3? Where? Oh, so in this case, the question was, where do we do L3? I'll let Mark field that one.
So the question, yeah. So with L3, Aconda is actually providing the L3 service, and the way Aconda works is Aconda will distribute the router, the logical router instance. Will actually instantiate the logical routers within the fabric. So in the case of Dream Compute, they're based on service VMs. So those VMs are actually running alongside other workloads already in the Nova Compute cluster. So in terms of upgrades, it's actually pretty easy because you can go through, you can update the control plane, and also with DreamHost itself is you can take that image in the appliance that's used for routing and actually do a rolling upgrade over time and replace those, in a nice seamless way and keep traffic up.
So, are they running with a service?
Microphone.
Microphone.
Oh,
Please.
are they running in a compute node on each, as a service VM in each compute node, or?
They're running on some of the compute nodes, not on every compute node. So within the configuration, you have the router. They can be paired with VRP, and so you can get failover, and you can go through and roll them and upgrade one at a time. But it's really depending on how they're scheduled within the compute cluster. So likely, yes, you do have them, but not every tenant's traffic may not necessarily be on the same node as its router.
Okay. So I'm trying to understand the packet flow. And the other question I had was, how do you allocate the local VLANs on each rack? What do you guys use for that? Because I think the example was 155 or something of that sort.
Yeah, so the local allocation is basically when it comes time to bind the port onto the host, the driver will go through and look at the available VLANs for that particular hypervisor and then select one within the allowed range and then mark it as in use. And then so it will repeat that process on, and so that gets you the first, like if you spin up a VM, when the port's bound, it's going to allocate and bind it all the way up to the switch, and then when you spin up another endpoint somewhere else, it's going to do the same thing. But because the pools for values are different between each host, you may get the same one, you may not. It's kind of unpredictable that way, but...
But then would each compute node do the same allocation in the same rack, or would it be different on each compute node? So let's say I have a VM on network 1 on compute 1, and then on compute 10, the same VM on the same subnet comes up.
Yeah, so that's actually kind of one of the more interesting features.
I can talk to that a little bit. The way the Linux bridging model works is you essentially have interfaces, right? Like normally ETH0, ETH1, ETH2, whatever. We call them SWP1 for switch port. But if you create a VLAN, basically you're creating a sub-interface. So VLAN 100 on ETH0 would be ETH0.100. And so this is kind of a separate interface. It is a separate interface. And so if I create a bridge, I can very easily bridge ETH0.100 with ETH1.200. And so now I can choose whichever VLAN numbers I want, as long as I kind of keep track of them and make sure that all of the VLAN numbers in that rack that I want to be on the same network are connected to the same bridge. And then to connect it to other racks, we connect a VXLAN interface into that same bridge. And that has the VNI for that virtual network for all, and that is global. But of course, that space is 24 bits, so you have a lot more of those.
interesting. I didn't get that, but So the other question I had was, you guys are using Linux Bridge, so what happens to security policies and ACLs and all that stuff?
So
Because
security groups are spoofing all the standard things all the standard features that you find now work as expected within Neutron.
So, but on Linux Bridge, how do you apply the OVS flows and all that stuff?
Sorry, what was the last?
So, I meant to say the Neutron security rules and stuff without OVS, how do you enforce those with the Linux Bridge?
So the interesting thing right now is if you're running OVS today from the reference implementation in Linux Bridge, they do the same thing. They're using NetFilter to enforce all the security group policies.
Okay. And the other question I had was, so you talked about the VX SND, right? Or those services. How do you replicate state in case of failure? Or for example, let's take the case of a VM migrating from one rack to another rack. How do you determine the topology there?
Yeah, so Neutron, OpenStack knows when it migrated a VM from one rack to another, and it tells Neutron. So it'll see the VM disappear in one and pop up in the other. And so then the new VTEP will register its interest with the database and will show up, and the old one will eventually age out. And so for a brief period of time, the packets will be unnecessarily replicated to the old destination, and they'll just be dropped there by the hardware.
Okay. And then the mesh you create within your switches, does it happen automatically, or is it, or how do you detect? Let's say if I bring up a new rack, for example, how do you connect to?
So all the racks are connected to the spine layer, and it's just a routed mesh. So you can use OSPF, you can use BGP. We're using BGP unnumbered in the DreamHost case, and I forgot to mention that the reason that config file for BGP was so simple is because instead of having to assign a subnet to each pair of interfaces between routers, you just give each router switch a single IP address, and it uses that to communicate with all of the other kind of routing protocols.
Okay. And the last question I had was, in the ML2, I saw a bunch of switches. Yeah. So do you, when I make a Neutron API call, do you talk with each of the switches to provision? Is that right, or
yeah.
is my understanding right, or?
So you found one of our hacks. Yes, today we would send it to all of them. We're working on a change to learn back from the individual switches which hypervisors are attached to them, and so then we can prune it and only send it to the ones that need it. But for relatively small deployments, having to replicate a short message 32 times is not a big deal.
But yeah, the rollback is a problem though in case things fail.
Sorry, what's that?
In case things fail on a 32-node switching, if two of them fail for whatever reason, then you'll have to start rolling back on all the rest of them, right?
I'm not sure I understand this.
I mean, when a Neutron API call comes in, if you're talking to, let's say, 32 switches in your fabric, you need to take off transaction rollback and
you want to create
atomicity and
so we're gonna clean that up a bit.
Cool. Thanks.
Thank you. Right there. I'll repeat the question while the microphone.
So the question is, you showed that there is a cumulus mechanism.
Here we go.
Yeah, no, thank you. So the question is, in the slides you show a cumulus mechanism driver that, if I understood correctly, is the software element that makes the configuration on the cumulus switch so that the VLAN is mapped to the VNI.
Yes.
Okay. Now, what is not clear to me is this mechanism driver is already upstream in OpenStack, or if you get it with when you buy the Cumulus Linux license, or if it is yet another product.
So it's not upstream yet. It's up on our GitHub. You can download it today. We're working on upstreaming it. Right now, you download it from our GitHub and then copy it into your plugins directory or ML2 mechanism drivers directory. But it'll be upstream soon.
Okay, so it's so new that it's not been published yet.
Well, it's published on our GitHub. It's not been upstreamed yet.
Okay. Yep. And so all the documentation, it will be integrated on the Cumulus documentation, or?
Well, it'll probably be in the Cumulus documentation, and also when it's upstreamed, it'll be in a different repo now because the mechanism drivers, the ML2 mechanism drivers, have been split into different repos. So the core Neutron no longer has any vendor drivers in it.
Okay, thank you.
What's the actual, from Neutron's perspective, what is the network type of the tenant network? Is it still a VXLAN segmentation ID, and then, or is it a VLAN
So
segmentation ID?
the network type will report back as VXLAN. From the tenant's perspective, they'll see it as a VXLAN network.
And that makes sense because the VLAN numbers could be reused in different racks. So the only number that uniquely identifies a logical network is the VXLAN VNI.
Okay, so and so at that point, are you eliminating the whole VXLAN tunneling between virtual switches, and it's just basically going to do all that stuff, but directly through the TORs, right?
Yeah, the virtual switches only work in terms of VLANs. The bridging between VLANs to VXLANs happens in the top of rack switch.
Okay.
Is there any question in the back? Sorry, could you repeat the question on the microphone? I couldn't
So
catch
when
it.
you have two different logical switches within the same tenant connected to a neutron router, which in this case is going to be an Akanda router, the packets will have to traverse the entire fabric, reach the Akanda router, get routed, and come back in, right? There's no like distributed routing.
So in this particular case, if you're routing between between two network segments of the same tenant attached to the router, yes, it will traverse the router, or it will traverse the two routers. Where it's not DVR. You know, in other modes you could run DVR on it, but and for this particular case, that's not, because of some other operational concerns. Akanda makes it easier in terms of rolling out new appliances. That was kind of the choice there.
Just one more other question. In this current deployment, how many physical interfaces does each server have? Does it have like two 10 gig interfaces connected to two Cumulus switches, or is it?
So this particular deployment is on the data plane side, single attached. So there's one connection from the top rack switch going to the server for carrying kind of tenant traffic. It's kind of more of a public cloud use case. We can actually support MLAG, which you end up with two top rack switches, and so they're paired as an MLAG pair. They appear to be a single switch to the hypervisor, just shows up as a bond, and then the same L2 to L3 transfer happens in the pair of top rack switches. So now the rest of the network is still L3, so the MLAG is limited entirely to a single rack. So you don't have that looping problem you have when you build large MLAG networks.
So with MLAG, you would be able to support this entire architecture that you just mentioned.
Yes, so a new feature in 2.5.4, Cumulus
Okay.
Linux 2.5.4, is the ability to run VXLANs and MLAG at the same time.
Okay, thanks.
How does the north-south traffic work from the service VM? Does it go over a VXLAN tunnel and just pop out on the WAN somewhere, or?
Yeah, so there's a L2 gateway currently in use, and that connects into the rest of the routing infrastructure inside of DreamHost. One of the two things with Akanda is each of the individual service VMs is actually speaking BGP north to announce reachability information for the tenant segments. So within that information, it's learned, and so you get routing both ways.
Any other questions? One over there. Oh, yeah. It's close to the mic. You're next.
Sorry. Is there a roadmap to have distributed layer 3 at the top of rack switch? So instead of just doing bridging from VLAN to VXLAN, can you support routing as well?
Well, so the current common hardware platforms, the forwarding ASIC chips, can't route once a packet has been decapsulated. Today, no. New chips are coming that will support being able to route out, and then we could, in some configurations, have that tenant-to-tenant traffic be hardware routed as well. But today, you have to bounce through the VM or through an L3 agent if you don't use the Conda.
Thanks.
So coming back to what you referred to as your little hack by addressing all the switches with the port information for the hypervisor, as far as I can remember in the configuration, you specified on the hypervisor a particular port where you are connected to the upstream and all the switches. So if two hypervisors are connected to the same port on different switches, how do you differentiate? I mean, for something like P6,
I'm having a little
So
trouble.
the question, if I understand it right, you say if two hypervisors are attached to the same front panel port on different switches, how do we differentiate them? So within that, the driver and the way it talks to the REST API is the switch learns the host attached to it, and then when it comes time to bind, when we flood the switches with information for binding, we're able to say if you have this host attached, the switch will know which front panel port it is, so that way you can actually have different.
Are you asking how the switch knows which hypervisors are on which port?
you're using LLDP or
Yeah,
something like
today we use LLDP. You can also configure it statically with the config file if you don't want to use LLDP for any reason.
Okay, understood. No, I was just a little bit confused because
since
there was
there's
an actual port in the configuration mentioned.
Yeah, so today, if you don't specify the list of hypervisors, it assumes you're using LLDP and tries to connect to the LLDPD. It does make sense to me to have the L2 agent that's running on the hypervisor report up to the switch it's attached to, who it is, but that's not there today.
Mm-hmm. Okay.
I guess.
Oh, we have a question over here. So how do we handle IP multicast traffic? So the routed fabric, the physical network, does not handle multicast. So all of the problems that are associated with routed multicast are just go away, right? You don't have to run PIMSIM or any of the kind of multicast routing protocols. And so the way that then gets handled is that the head-end replication will take care of it. So if a VM sends a multicast packet, it goes up to the top of rack switch, which then knows, hey, the following other 6 racks have other VMs that are in this logical network. I need to send that multicast packet to all of those other top of rack switches, so then it can send it down. And so the replication, it actually works fairly similar, and it actually uses the same hardware inside the chip that is used in multicast. That's how we do the head-end replication in hardware. So it's very similar in terms of how it happens, but it means you don't have to run another routing protocol.
But the VNI only track the layer 2. If you have,
we don't do IGMP snooping
across
today.
different VNI, I mean.
Different VNIs are totally independent. So a multicast packet on one VNI will only go to other racks that are interested in that VNI. It will not go to other racks.
Yeah, but if you have multiple VNI belong to the same tenant and they're in the same IP domain, they could have a layer 3, the IP multi-group, right?
Well, you'd have to have you'd have to have a multicast router between the different VNIs associated with a single tenant.
Okay, so they're
different L2 networks.
Are you going to run the PIM or those kind of protocols?
You could. I'm not sure. I'm not sure I understand the use case. It seems, if you have a bunch of VMs that want to multicast with each other, the easy thing to do is put them in the same VNI in the same logical network.
Okay.
You're good?
Okay.
All right.
Well, thank you very much.